Okay, guys, so welcome back to your gravitational chapter. Today we will be continuing with the last topic of the unit gravitation. Today we will discuss the geostationary or geosynchronous satellite and the polar satellite. These two are the types of artificial satellite. In the previous section, we learned about satellite, escape velocity, orbital velocity of the satellite. But here, we will mainly focus on uh, these two types of satellites, polar and geostationary, their uses, their differences, and what are the orbits around which both of these types of satellites revolve around. So let's first start with the geostationary or geosynchronous satellites. So as you can see in this picture here, that a satellite is revolving around the earth in such a way that the satellite seems to be at rest. Let's say the continent they have taken here in the picture is Africa. There's a I would say South America. So at the point here, let's say there's a country called Chile. So here, Chile has launched a satellite in the Earth um, from their station. So in this condition, you can see that for from that point of the country, the satellites will seem to be at rest, although both Earth and satellite are moving. Yeah, so satellite which is at rest with respect to the Earth is called geostationary satellite, as the name suggests, geostationary satellite, or synchronous. It is in synchronization with the rotation of the Earth. Okay, the revolution of the satellite is in synchronization with the rotation of the Earth. That's why we can say synchronous as well. So there are some following conditions which a satellite must follow so that it becomes a geostationary satellite. Otherwise, it won't revolve like this. So these conditions are: first, the time period of the satellite in circular orbit around the Earth in the equatorial plane. Remember that this satellite, geostationary satellite, is revolving in a plane. This plane is the equatorial plane. Let's say we know that this is the equator. So the satellite must lie in the equatorial plane and no other plane. Okay, that will be a different kind of satellite. So this has to be the equatorial plane, and its time period of revolving around the Earth should be equal to the rotation period of Earth, that is 24 hours. They must have both have same time period. And the direction of rotation, see, it's very important that the direction of rotation of the satellite about its axis must be same as that of the Earth. Earth rotates about its axis from west to east, okay, anti-clockwise direction. As you can see here, it is rotating in anti-clockwise direction. That means the satellite must also rotate in anti-clockwise direction with the same time period. Okay, this is what we call as it moves in the same sense as the Earth, from west to east. Okay, one more point here, that the orbit of the geostationary satellite is known as the parking orbit. It is as if you have parked the satellite on this orbit. Okay, from the surface it will look like it has been parked in the sky. So we will say that this is the parking orbit of the satellite. Now, as we have already discussed, that the time period of the revolution of Earth satellite depends, they have to be same. Now, we have studied in the previous lecture that the height of the geostationary satellite above the equatorial plane must be about 36,000 kilometers. This is the height that we have find out that will be important for the satellite to be launched, such that it will behave like a geostationary satellite. This is the minimum height required. It's a very large distance actually. So geostationary satellites are actually about 36,000 kilometers away from the surface. So we already know from the formula that height of the geostationary satellite from surface of the earth can be calculated by using this equation here. H is equal to t square time period r square small g for constant acceleration due to gravity divided by 4 pi square and cube root minus r. Now if you put all the values, you know the time period should be 24 hours, that is 34 into 3600 seconds, and radius of earth, this is the radius of earth, capital R, and small g is 9.8 meter per second square. If you put all the values here and solve it, you can figure out that h will be equal to around 35,930 kilometers, which is approximately 36,000 kilometers. That's how we figure out the height which is required for a satellite to be geostationary. Thus the height of ordinary orbit of geostationary from the surface of Earth is about 36,000. Geosynchronous orbit of the satellite is shown here, as you can see in the figure here as well. This is called as the geosynchronous orbit or the parking orbit. This is, the plane must be the same, equatorial plane. The satellite can be only in the equatorial plane. These are the conditions, 3 conditions that you need to remember, and you can also prove now how it is the height for the satellite is around 36,000 kilometers. You can use this formula to derive that. Now let's now understand the uses of the geostationary satellite. There are very interesting uses of the geostationary satellite. So these are the conditions that we have already discussed. Now uses. They are used for communication purposes. These the main purpose of geostationary satellite is communication. Like you can transmit the radio signals. The radio they were prevalent in the previous decade. Radio and right now TV programs or even your OTT programs, the internet even works with this technology by sending telephone signals across the oceans. This is also one of the uses. So that's why remember that a geostationary satellite is also called as communication satellite. And second use is geostationary satellites are used for weather forecasting. They are used for weather forecasting. I will tell you that why geostationary satellite is a good choice for weather forecasting, but there's another better option also. Now, the geostationary satellites are employed for studying the upper region of the atmosphere. Obviously, we know that the orbit, what we say, the parking orbit, the geosynchronous orbit is around 36,000 kilometers. So upper atmosphere of Earth can be studied from there because it will have a bigger picture from the up above. And very importantly, these are two things that the scientists are using these satellites for. They are used for study radiations, solar radiations. Remember that the sun continuously releases radiations. Okay, sometimes they are very dangerous also, but our atmosphere takes care of that, like the ozone layer. So let me give you an example. Like from the sun, let's say there is some solar flare. It's a very high frequency, some waves are coming from the sun, solar flare it is called. So if you have a geosynchronous satellite revolving around the earth, and one of these detectors are phased around the sun, we can predict that a solar flare is coming before it reaches the earth's surface, so that we can have some protective measures for that. Yeah, so this is one of the uses to study the sun and its radiation. And also there's a very interesting topic in physics that if you have proper detectors on the satellites, it is observed by scientists and researchers that there are cosmic radiations coming from the interstellar space. They are everywhere. They are very difficult to be detected, but they can be detected from this clear sky, or you can say here it is vacuum. So there is no atmosphere to stop it from detecting the cosmic radiations. They are, let's say, very different kind of research, but they can be detected. These waves, cosmic radiations, can be detected using this geostationary satellites. Okay. Okay, and now let's study a little bit about the rockets. So space rockets are used to launch the satellites. And remember, they're always launched from west to east, as we have already discussed. West to east should be the direction of the satellite also, just like the Earth. And in the equatorial plane, for obvious reasons. And when the space rocket is launched from the west to east, the linear speed of the Earth, due to its motion, also gets added. Okay, let me explain that with the figure. Let's say you are launching the satellite from, let's say, America here. So if you're launching it from here, you will launch it in such a way that you will launch it from west to east, so that the Earth's rotational speed will also get added. The momentum will get added to the satellite as well, so that it will be little easy for the satellite to be launched in the sky. So rockets are launched like this, from west to east. And equatorial plane, we know that the radius of Earth is maximum at that point. Yeah, so the linear speed will also be maximum in the equatorial plane. So the speed of the rocket will be maximum if you launch it in the equatorial plane only. Okay, one more thing, very interesting point, before we go to the another type of satellite is in the uses. So in the uses, we studied about transmission of radio and the TV program, TV or microwaves. So let me explain that in little more detail. Okay, yes. So the need of geostationary satellite for long distance communication. See, there are two types of long distance communication, First is that we used to have radio. Okay, you used to have radio transistors. So we used radio waves. In order to transmit the radio waves, we used the transistors, or we say the radio. So radio waves travel in straight line. Remember that the radio waves which are there, they travel in the straight line like light. But when radio waves are transmitted from, let's say, a point on the Earth, then these waves cannot reach the very far away point, that is the B, because of the Earth's curvature, right? They cannot directly, because radio waves only travel direct, straight line. So they cannot reach the receiver if you are just transmitting them. So what is the need? So radio waves used to broadcast radio programs. Like frequency of those radio waves is from 2 megahertz to 10 megahertz. This was the frequency range for radio waves. Alright, so we know that in the atmosphere there is ionosphere. Now here comes the use of ionosphere. Very important and very interesting. See, among the very different 4 to 5 layers of the atmosphere, ionosphere is very helpful in sending the radio waves, because it can reflect the radio waves. The radio waves are reflected by the ionosphere, and the reflected radio waves reach the receiver. They get reflected and they reach the receiver at point B. So there the ionosphere is helping. On the other hand, remember, now we'll be talking about the microwaves. So microwaves are actually having a very high frequency as compared to radio. Radio waves have low frequency, but microwaves have high frequency, and they don't get reflected by the ionosphere. See the point here, that how ionosphere cannot help to in transmission of the microwaves. They can only transmit the radio waves from 2 megahertz to 10 megahertz. But for our TV signals, high frequency waves are used, have to be used, microwaves, because it has video, audio, both. So television signal can be transmitted from one place on the earth to the distant place on the earth if transmitters and receivers are always in sight of each other. The same thing is there, like the transmitter and the receiver has to be in the line of sight. It has to be in a line of sight transmission. This type of transmission or of signals or message is known as line of sight transmission. So there is a catch here. So ionosphere can't help us, and it has to be a line of sight, and we know that earth is curved, so a line of sight communication can only work up to a point. If we have to send a signal from one part of let's say from Kashmir to Kanyakumari, we won't be able to do that. So line of sight transmission between the main transmitter, let's say there's a transmitter in Delhi, and the main transmitter on the curved surface, if earth is possible, if number of repeaters are there. Remember that repeaters are like amplifiers. Yes, this is the picture here that can help us to understand this. So a main transmitter and the main receiver on the curved surface of earth, line of sight transmission is only possible if you have number of repeaters, just like it here. This is line of sight communication. This repeater will amplify the main transmitter signal, microwave signal, and then it will go to the another repeater and then the main receiver. Okay. Now, however, repeater cannot be erected in oceans. Let's say you have to send a signal from India to Africa. So there is an ocean between them, and there are sometimes a mountain where you cannot erect a repeater antenna. So what do you need? To overcome that problem, we require a big microwave repeater in the space itself. See how we have overcome this problem. We require a big microwave repeater in the space itself, which remains fixed at one place. Instead of erecting a repeater in the ocean, which is not possible always, or maybe some Himalaya mountains are there, so you will try to make a microwave repeater in the space, so that there will be direct line of sight communication, okay, or transmission. So to overcome this problem, to achieve this type of repeater, first communication satellite, that is what kind of satellite? Geostationary satellite, was launched in 1958. So satellite communication is like the line of sight microwave transmission. Remember that for satellites were used mainly with for the purpose of geostationary satellite, for the line of sight microwave transmission. So in this case, a beam of microwave containing message is projected towards the satellite itself. On the other hand, the geostationary satellite will now do what? It will reflect these waves towards the receiver. Thus, geostationary satellite act as big microwaves repeater in the space. Clear? Yes, this is how it works. There is a transmitter, there is a receiver, and instead of there are repeaters on the surface, which is not always possible, we have a geostationary satellite. See, and it's very important that geostationary satellite should be like a stationary object in the sky for that transmitter to continuously work, right? That's why geostationary satellite has to be there. Otherwise if the satellite is not geostationary, its position will change with time on the day, and it will be useless. So it has to be looking like a stationary satellite, just like I have shown here. It has to be stationary with respect to the point on the earth. So every nation has their own geostationary satellites. We have INSAT, Indian satellite, INSAT. Okay. Yeah. So this was the all about geostationary satellites. Now let me take you to another kind of satellites, that is the polar satellites. Polar satellites are also very interesting. So a satellite that revolves in polar orbit around the earth is called polar satellite. The polar orbit passes over the north and south poles, up and down, north and south poles of the earth, and it is usually, see, there's a difference, only 250 kilometers to it. Okay, so here let me show you through the picture. Yes, here, look, the polar satellite. Now we are talking about the polar satellite. See, they revolve around the north and south poles of the earth rather than the equatorial plane. These type of satellites are the polar satellites, because their orbit is around the poles, north and south. So they are also used for communication purpose, and they're about I believe 250 to 400 kilometers above the surface. And on the other hand, low to medium altitude satellites in polar plane pass over north and south poles. These are the polar satellites. So the orbit in which a satellite move is known as polar orbit. This is known as polar orbit, and this is polar satellite. So the angle between equatorial plane and the orbital plane is 90 degree. This is the equatorial plane, and this at 90 degree we have the polar orbit. Their angle between each other is the 90 degree angle, as you can see here as well. Yeah, so this is the polar orbit. This is very interesting thing about the polar satellite. It is very different from the geostationary satellite. At different points of the day, it will be at the different positions, because Earth itself is rotating about its axis, right? So although they are revolving around a single orbit, the Earth itself will be, let's say India was there at this position in the morning, and a satellite was here, so it took the pictures of the Earth or the India nation. Now after 5 hours, Earth will be somewhere else. The Earth's the particular continent will be here somewhere, and the satellites will be here somewhere. So maybe in the night, if it comes back, it will be a different country in front of the polar satellite. So in a way, as you can see here, that in a way polar satellite can look at many parts of the earth rather than just one part of the earth. So polar satellites are actually not used for communication purpose, because they're not available at a particular point on the surface. They are not visible every time. So they are actually used for remote sensing. So these are called as remote sensing satellites. Remember, it's a very important point that remote sensing satellites are called as the polar satellites. And what is remote sensing? Remote means distant, like you study something without touching it. So remote sensing, you study a thing far away. That is the remote sensing. It's a technique used to collect the information about any object without actually touching the object. So if a country want to survey the area which is inaccessible to them, for maybe for spying purpose, they will use the polar satellite. Okay. Yes. So let's understand about the uses of polar satellites. So Polar satellites are used to record the land and sea temperatures also. Land and sea temperatures, take pictures of clouds, and make forecasting for the climate change. See, it's an important point here. Although geosynchronous also takes a picture of upper atmosphere, but polar satellite I think is much better for the forecasting, because first thing, it is closer to the Earth's atmosphere, it is within the Earth atmosphere, and this is more reliable than made by the weather satellite put in geostationary orbit. Okay, it is more reliable, and they are used to monitor the trend of greenhouse effect. Greenhouse effect, how the climate is changing, all these things are detected by the polar satellite. Okay, now they are used to monitor the trend of greenhouse effect. For example, some years back, it was observed by a polar satellite, British polar satellite, that there was a hole developed in the ozone layer because of the uh, extreme emission of the uh, uh, greenhouse gases. So it was detected by the polar satellite. Polar satellite may be called as monitoring or weather satellite. Remember that polar satellite is also called as weather satellite, but the geostationary satellite is called as the communication satellite. Now, the polar satellites are used for military purposes. These are for obvious reasons, because polar satellites can take pictures of different locations of the Earth. So all military nations, they use these satellites for military purpose. They can keep an eye on the movement of ships, troops, and vehicles, and spying and surveillance. Yeah, and they are used for remote sensing, that we already know. So this was all about the polar satellites. Okay, I hope you have understood both the satellites, their differences. So, okay. So now, last but not the least, these are the two questions that I would like you to try. Question 1 is, in a spaceship moving in gravity field region, the astronaut will not be able to distinguish between up and down. Let's say in a satellite, if you are in a geostationary satellite like the International Space Station, ISS, if you are in that, you won't be able to distinguish between up and down. I would like you to explain in the comment sections why would that be the case. And for the second question, we have the geostationary satellites moves in orbit of 36,000 kilometers. This is the orbit of radius given from the surface to Earth. Now, the radius of Earth is 6,400 kilometers, and the mass of Earth is 6 into 10 to the power 24 kilogram. You have to calculate the gravitational potential at the position of the geostationary satellite. Please try to solve this and give your answers in the comment section.